Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1667 publication of the Arithmetica Infinitorum by John Wallis represents a monumental exercise in mathematical intuition and procedural audacity. It stands as a work whose conclusions and innovative techniques possess a power that far exceeds the rigor of their own demonstration. This essay provides a direct and systematic evaluation of the internal claims, arguments, and specific conceptual frameworks presented within the Arithmetica Infinitorum. The analysis proceeds through the book's major logical stages, from its foundational propositions concerning series to its celebrated derivation of an infinite product for the constant pi. The focus remains squarely on the content of the work itself, examining the mechanisms Wallis employed, the evidence he marshalled for his increasingly bold assertions in profound intellectual courage manifest in his extension of arithmetic reasoning into the uncharted territory of the Section 1. The arithmetic transformation of quadrature and the principle of induction. The introductory propositions of the Arithmetica Infinitorum establish Wallis' primary methodological claim that the geometric problem of finding the area under a curve, a process known as quadrature, can be comprehensively reframed and solved through purely arithmetic means. Wallis commences his argument by examining the ratio of a series of powers to a series of the maximum term raised to that same power. For instance, he considers the sum of the first few squares, as in 0 squared plus 1 squared plus 2 squared, and compares this sum to the sum of the maximum term squared, as in 2 squared plus 2 squared plus 2 squared. The ratio he finds is 5 to 12. By extending the series to include 3 squared, the ratio of the sum of squares to the sum of the maximum term squared becomes 14 to 36. Wallis presents these results in tables. Making the underlying pattern visible, he observes that as the number of terms in the series increases, this ratio consistently approaches the value of 1/3. His central argument in this section hinges upon a technique he terms per modum inductionis, or by way of induction. Having demonstrated the pattern for squares, he repeats the process for cubes, finding the limiting ratio to be 1/4, and for fourth powers, finding it to be 1/5. From this finite set of observed cases, Wallis makes his first major inductive leap. He posits that for any positive integer k, the ratio of the sum of the first n terms raised to the power k to the sum of n terms of the maximum value raised to the power k will approach 1 divided by the quantity k plus 1. As n becomes infinitely large, the logical foundation for this universal claim is analogy. The evidence presented is the consistent behavior across the first few integers. The argument's force derives from its empirical consistency within the tested domain, a style of reasoning that prioritizes pattern recognition over deductive proof. This section's core achievement is the successful conversion of Cavaliere's method of indivisibles, which was fundamentally geometric and reliant on visual intuition about lines and planes, into a systematic, algebraic procedure. Wallis' claim is that the language of ratios and series provides a more powerful and generalizable tool for problems of the infinite than the language of geometric figures. The validity of this claim, for the domain of positive integers, is robustly supported by the results his method generates, which align perfectly with those found through established geometric techniques. Section 2. The generalization to fractional and irrational exponents. Having established a rule for integer powers, Wallis proceeds to make the most consequential and speculatively brilliant claim of the entire work. He asserts that the relationship he discovered must hold true for all exponents, including fractional, negative, and irrational numbers. The mechanism for this extraordinary generalization is an implicit belief in what would later be called the principle of continuity. Wallis' argument is one of pure formal extension. He has produced a sequence of results for exponents 1, 2, 3, and so on. He perceives this sequence as a manifestation of a universal law of quantity. Therefore, he concludes, It is inconceivable that this law would suddenly fail for an exponent of, for example, 1/2 or 3/2. He is effectively claiming that the algebraic form of the result, 1 divided by the quantity k plus 1, is more fundamental than the specific integer values of k from which it was to. The evaluation of this claim reveals the heart of Wallis' mathematical philosophy. There is no formal proof offered for this stupendous leap. The evidence is entirely unlogical. Wallis is arguing that the harmony and regularity observed in the world of integers must, by a principle of cosmic and mathematical consistency, extend to the world of fractions. He treats the sequence exponents as a continuous entity and assumes that the function governing their associated quadratures must also be continuous. This allows him to assert, for instance, that the quadrature of a parabola with an exponent of 1/2, what we would call the curve defined by y equals the square root of x, is governed by the same rule. Applying a formula, he correctly deduces that the area is given by 1 divided by the quantity 1/2 plus 1, which yield 2/3. This result was known, but Wallis' method provided a derivation that was purely algebraic and part of a grand, unified system. The critique of this section's claim centres on its complete lack of deductive justification. Its genius, however, lies in its profound fruitfulness. Wallis is operating on a deep-seated faith in the interconnectedness of mathematical structures, a faith that allows him to write down correct results for which a rigorous proof would only emerge a century later. The claim is a triumph of intuition, demonstrating how a powerful new idea can be correct long before it is proven. Section 3 Interpolation as an engine of discovery for the quadrature of the circle. The apex of the Arithmetica Infinitorum's argument resides in its application of these principles to the notoriously difficult problem of the quadrature of the circle. Wallis recognized that finding the area of a quarter circle of radius 1 is equivalent to finding the area under the curve defined by the equation y equals the quantity 1 minus x squared all raised to the power of 1/2, evaluated from x equals 0 to x equals 1. Within his newly generalized framework, this is a problem of evaluating his quadrature formula for a complex term with a fractional exponent. A direct application of his earlier method proves computationally intractable. In response, Wallis devises his most ingenious and audacious technique, interpolation. He constructs a two-dimensional table of values. The table represents the reciprocal of the integral from 0 to 1 of the quantity 1 minus x to the power of 1 over p, all raised to the power q. The columns correspond to different integer values of p, and the rows correspond to different integer values of q. For integer values of p and q, the entries in this table can be calculated directly using extensions of his method of series. For example, O where q equals 1 generates the harmonic series 1, 2, 3, 4 and so. A row where q equals 2 generates the triangular numbers 1, 3, 6, 10. Wallis meticulously calculates these integer-based values, filling his table and revealing intricate numerical patterns running both horizontally and vertically. The problem of the circle's quadrature corresponds to the entry in this table where p equals 2 and q equals 1/2. This is a point that lies between his calculated integer. His central claim in this section is that the value for this intermediate fractional case can be determined by discerning the law that governs the sequences of numbers in the table and interpolating the missing term. He observes the ratios between consecutive terms in a given row. He then assumes that this same proportional relationship must hold for the column containing the value he seeks. It is an act of breathtaking intellectual confidence. He is effectively treating the discrete table of numbers as a sample of a smooth, underlying function and is attempting to divine the nature of that function from the sample points. He looks at the sequence for p equals 2, which contains the unknown value he calls square bracket, and sees the numbers 1, square bracket, 3/2, 15/8 and so on. By analysing the structure of all the other rows and columns, he intuits the rule for generating the intermediate terms. The methodology is entirely heuristic, a form of highly educated guesswork guided by the profound structural regularities he has uncovered. It is a claim that the inherent order within mathematics is so powerful that a missing piece of knowledge can be reconstructed by observing the shape of the knowledge surrounding Section 4, the infinite product, as the culmination of the arithmetic method. The direct result of Wallis interpolation is one of the most beautiful and celebrated formulas in all of mathematics. The Wallis product for pi, having interpolated the value for the square bracket term in his table, which represents the reciprocal of the area of the quarter circle, he performs the algebra to solve for that area. This area is known to be pi divided by 4. The final expression he derives from his interpolation is a claim about the fundamental arithmetic structure of this transcendental number. The claim is that pi divided by 2 is equal to an infinite product of rational numbers. This product is structured as 2 times 2 divided by 1 times 3, all multiplied by 4 times 4 divided by 3 times 5, all multiplied by 6 times 6 divided by 5 times 7, and so on, continuing infinitely. The evaluation of this claim must appreciate its dual nature. As a mathematical statement, it is a profound and correct assertion, expressing pi not through geometry or measurement but as the limit of a perfectly regular, infinite arithmetic process. It reveals a deep, hidden connection between the circle and the integers. As the culmination of Wallis' method, the product stands as the ultimate vindication for his entire chain of reasoning. The astonishing elegance and correctness of the final formula served in the 17th century as powerful evidence for the validity of the questionable steps that led to it. The inductive leaps and the audacious interpolation were, in a sense, retroactively justified by the beauty and utility of their conclusion. The claim of the infinite product is the capstone of his argument, demonstrating that his arithmetic of infinites could produce new, profound, and verifiable knowledge that was inaccessible through conventional means. The formula itself is a testament to the power of his system, a concrete piece of new mathematics born from a methodology that valued in the logical insight and structural beauty as legitimate tools of discovery. Section 5, the method's ramifications as seen through contemporary scrutiny. The reception of Arithmetica Infinitorum provides a crucial lens for evaluating its internal claims, particularly the tension between its inventive power and its logical deficiencies. The work provoked immediate and intense discussion across Europe. The French mathematician Pierre de Fermat, a figure deeply committed to the traditions of rigorous proof, famously challenged Wallis on his methods. Fermat's critiques centred on the reliance on induction. He requested that Wallis provide a more formal, deductive demonstration for his general conclusions about series, pointing out that observing a pattern for 3 or 4 cases failed to constitute a proof for all cases. Fermat's request highlights the central vulnerability of Wallis' argument, its foundation in analogy. This contemporary scrutiny affirmed that while Wallis' results were often correct, their logical underpinning was incomplete from the perspective of classical deductive standards. Conversely, the work's profound influence on the next generation of mathematicians speaks to the perceived validity of its core conceptual claims. A young Isaac Newton studied Arithmetica Infinitorum with immense care. Newton saw the immense potential in Wallis' core ideas, the use of fractional exponents, and the method of interpolation, as a tool for discovery. Newton's own work on the generalized binomial theorem can be seen as a direct and powerful formalization of what Wallis had intuited. Newton took Wallis' table of values and his interpolation method and sought the underlying algebraic rule that governed them. The result was a formula for expanding a binomial raised to any rational power, which in turn provided a systematic, algebraic way to generate the infinite series for expressions like the one for the circle. In this way, Newton's work supplied the rigorous algebraic machinery that Wallis' project lacked. It confirmed the correctness of Wallis' claims about fractional exponents and provided a deductive basis for the results he had found through induction and interpolation. The reception, therefore, was twofold. It acknowledged the logical gaps in Wallis' presentation while simultaneously absorbing and building upon its profoundly innovative and fruitful claims, recognizing their fundamental correctness and their power to open up new mathematical Conclusion: the Arithmetica Infinitorum is a work of sustained intellectual brilliance, whose claims consistently and deliberately operate at the frontier of mathematical justification. A section-by-section evaluation reveals a coherent, argumentative arc, beginning with the foundational claim that arithmetic can supplant geometry in the analysis of infinites, and culminating in the astonishing discovery of the infinite product for pi. Wallis' core assertions: universal applicability of formulas derived from induction, the extension of integer properties to the fractional domain through a principle of continuity, and the power of interpolation to reveal unknown mathematical truths are all supported by a form of evidence that prioritizes pattern, analogy, and the aesthetic harmony of the results. The work's internal logic is not one of deduction but of algorithmic exploration and inspired conjecture. Its enduring significance rests on this very quality. The Arithmetica Infinitorum demonstrated that progress in mathematics could be achieved by a courageous exploration of new methods, even when their formal justification remained elusive. It supplied the essential algebraic framework and the conceptual confidence that proved foundational for the subsequent development of infinitesimal analysis, showcasing a pivotal moment where the imperative for discovery and generalization proved to be a profoundly effective guide to mathematical reality.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.